start the afternoon session. So it's my pleasure to introduce Malte Witte from the University of Regensburg, who will talk on non-commutative Iwasawa main conjecture for varieties over finite.
This is working. First of all, I want to thank the organizers for inviting me. And so the title of the talk is non-commutative Iwasawa main conjecture for varieties over finite fields. And before I start, let me introduce some general notation. So F is supposed to be a finite field of characteristic P. And L is a different prime. And X a separated scheme of finite type over the finite field F. The aim of this talk is to formulate Iwasawa main conjecture of the style of Coates, Fukaya, Kato, Schneider, and Van Jacob for varieties over for this scheme X of finite type over F. Let me just abbreviate the 5 people by CF KSV. So for certain admissible, so I use this word as well, L-adic Lie coverings of X. So, and I said formulate, but actually the nice thing about this case of finite fields is that in this case we can really prove something, actually everything. So most of the talk I will be spending formulating this conjecture, and in about the last 10 minutes then giving some details of the proof. So the first thing I have to tell you is what I mean by admissible Lie coverings. And I start with something more general. I talk about principal coverings in general. So, and this definition basically goes back to Grothendieck in SGA1. With the simple difference that in SGA1 you only consider finite groups, and now I generalize this to profinite groups. So a principal covering and I denote it by f y goes to x And G of X with Galois group or profinite Galois group G is a system of finite coverings Fu Yu goes to X, indexed by the open normal subgroups of G, such that the following conditions are fulfilled. So the first thing is that Fu from pardon? Oh, yeah, sure. Better? So the map Fu from Yu to X is finite, étal, and surjective. Second, you have a right action of the factor group G by U on the scheme Yu by X morphisms, such that the induced map from the disjoint union over copies of Yu to the direct product of Yu with itself over X is an isomorphism. And thirdly, well, the system is compatible. So if we have two open normal subgroups contained in each other, then you get a commutative diagram which is with a morphism which is G equivalently. So this is straightforward. Just to give you some examples.
G doesn't have to be a constant.
I beg your pardon?
G doesn't have to be a constant.
Well, in this case, I consider profinite groups which are just constant. Yeah, so they're constant. So examples. The first one, which is very important for me, is the following. I consider something called X sig. And X sig is nothing else than the base change of X to the field of all p power roots, L power roots of unity. So zeta L to the infinity. And gamma is the group generated by the Frobenius of F. So this is the geometric Frobenius of F. Which is then isomorphic to ZL. I think I have to tie my shoe. No. Okay. Another important example is if I take X connected. Then I can just take the étal fundamental group of X. with respect to some base point, and yu then the covering of X corresponding to the subgroup of U. But I also have some trivial examples. For example, I can take an arbitrary group and define yu to be just the disjoint union. So I don't exclude those examples. And finally, I just want to remark, if I take a principal covering in this sense, and a closed normal subgroup of G, and I denote by phi the projection map from G to G mod H, then I get a new principal covering, which I denote by FH Y mod H to X with Galler group G mod H and here Y mod H of V is defined as Y of phi minus 1, so the pre-image of V for an open normal subgroup in G of G mod H. And with this construction, I can say what admissible covering is. So an admissible covering for me is a principal covering with Galler group G of the following type. I have a semi-direct product of H, or of a group H, a closed subgroup H with gamma, such that this G is an L-adic Lie group. And the covering Y mod H to X with gamma is the cyclotomic covering that I defined in example 1. So much for the notion of principal coverings. The next thing I want to explain is well, something related to Iwasawa algebras and K-theory. So Iwasawa algebras, we've seen this in the last talk already. Yes. So the second point is Iwasawa algebras. K-theory. And again, some notation. So we already have seen the definition of the Iwasawa algebra, and I just changed the notation. So for me, the Iwasawa algebra of G is denoted by lambda G. So, and this was the inverse limit over the open subgroups of G of ZL G mod U. And G is here, as before, a semi-direct product of H with gamma. And in this situation, Ottmar Wenjakob has defined a canonical Urset and we don't need to know how it looks like, but we need to know that the quotient ring then exists. And this quotient ring will be denoted by lambda S of G. So there's some more notation coming. Let R be any ring with a unity. Then I define a category P of R. And this is supposed to be the category of perfect complexes. And let's say left R modules. And let me just recall what a perfect complex is. So a complex of left R modules is called perfect if there is a quasi-isomorphism with a bounded complex of strictly bounded complex of finitely generated projective R modules. So strictly bounded and Pn is finitely generated projective. Okay. So in particular, I can apply this to lambda G. And in this category P of lambda G, I'm interested in a subcategory, which I call PH lambda G. And this subcategory consists of those complexes and P lambda G, which are also in the category of, which are also perfect as lambda H complexes. Oh yes, and I should mention something about this, the morphisms in this category. So I don't localize at the quasi-isomorphisms. I really take the complex morphisms itself. And I need a third category, which I call PS of lambda G. Which is the same as the category lambda G, P lambda G. But now I want to call a quasi-isomorphism a morphism So I introduce a new notion of quasi-isomorphisms. So morphism of complexes will be called quasi-isomorphism in this case. And I call this morphism F. If the cone of this morphism is a complex in pH lambda G. So the important fact is
Age is fixed in this definition?
yes. So this S stands for the canonical OR set, which depends on H. So the important fact is these are actually Waldhausen categories. Which means they are categories with the good notion of exact sequences and of quasi-isomorphisms. And more importantly, we can assign K-theory to such categories. And this is done by the Waldhausen S construction. So to any Waldhausen category W, I can assign some topological space which I call SW, a connected topological space. Now I can define the K-theory of this category Kn of W to be the n plus first homotopy group of this space. And it turns out that this construction generalizes the Quillen K-theory. So let me just list some facts that I need about those groups. So K0 of W can be explicitly described. This is given by the abelian group generated by the objects of W. Modulo the relations defined by exact sequences and quasi-isomorphisms. K1 of W is in general much harder to describe, but what one can always say is if I take a quasi-automorphism, so a morphism which is a quasi-isomorphism between an endomorphism of an object in W, which is a quasi-isomorphism, then I get a class in K1 of W. Furthermore, if I take now the nth K-group of this category of perfect complexes of any ring, what I get is equivalent K-theory of the ring. If I now take the nth K-group of this category PH lambda G, what I get is a relative K-theory of lambda G in the localization at S of lambda G. And finally, for the category PS of lambda G, yes. If I take this here, what I get is the nth K-group of lambda S of G, at least if n is larger than 1, larger or equal to 1. And if n is 0, then I get the image of K0 of lambda G in K0 of lambda S of G. This is actually a very general statement that follows from the paper of Weibel and Yao about the localization sequence. No, because if you take just a commutative group which is not P torsion, but a finite commutative group which is not P torsion or L torsion, I'm sorry, then the whole group. Or wait, yeah, if you take a P torsion, P torsion commutative group, then the quotient ring should separate. It should, if you tensor with L, well, but maybe I'm not too sure about that, but it's not so important. So it could be that it's surjective always. Yeah, sorry. So if I localize at P, then I have a problem, yeah. But if P is not in S, then I might not have the problem. So this follows basically from the localization sequence of proved in the paper of Weibel and Yao. And actually from this there also follows that we have an exact sequence K1 of lambda G goes to K1 of lambda S of G goes to K0 of the relative lambda G lambda S of G, and then to K0 of lambda G, and finally to K0 of lambda S of G. And on this side, the sequence continues. And actually, one can, if one uses this description of Kn, then one can describe explicitly what happens with those elements of the type P of a quasi-isomorphism F from P to P, with P in this group PS of G, PS of lambda G. This is simply mapped to minus the cone of F, or the class of it. So that's all I need to know about K-theory. The next thing I need to talk about are adic sheaves. Actually, I only need it for lambda G, for the ring of lambda G. So I restrict to this case. So a flat, and my sheaves always will be flat, lambda G sheaf F on X is a system again of sheaves F and U with N coming from the natural numbers, and U the open subgroups of G, open normal subgroups of G, such that F and U is a flat, constructible étale sheaf of Z modulo Ln G modulo U modules, and the morphisms of the system induce isomorphisms ZL MZ G mod V tensor F and U to FMV for U contained in V and N larger or equal to M. So this is a direct generalization of the notion of ZL sheaves, which are classically considered in the Weil conjectures, for example. And this construction basically was already done by Uwe Janssen. So you get ZL sheaves if you take G equals to the trivial group. And what Uwe Janssen showed as well is that you can define something like compact continuous étale cohomology for those sheaves. So, and in fact, those complexes that calculate the compact étale cohomology turn out to be perfect complexes. Both if you take the compact étale cohomology of F and over X and over the algebraic closure of X, so the base change to the algebraic closure of F. So they are both objects in the category P of lambda G. And here you have the geometric Frobenius acting. And what you can also show is that you can choose representatives of those complexes or such that you get an exact sequence. With here the 1 minus the geometric Frobenius. Now, if I start with a ZL sheaf, then I can get a sheaf of a lambda G sheaf in the following way. And that's the last thing I need before I can state the theorem. So if I start with a ZL sheaf, and take any principal covering, then I get a lambda G sheaf, which I denote by F lower star, F upper star of F, and which is defined in the following way. So I have to say what F lower star, F upper star of F and U is. And this is defined by Fu lower star, Fu upper star of Fn. So this is the same as the system Fn, where n runs to the natural numbers. Just a remark, if you look at the stalks of this sheaf in some geometric point x, and this is isomorphic to lambda G tensor ZL with a stalk of x. but well, this isomorphism is non-canonical. Okay, so now I can state the Iwasawa main conjecture for those types of sheaves. So I return to the admissible coverings that I defined in the beginning.
Non-canonical is what are the choices?
So basically you need to choose one special point of the base change of x, or of the point x to y. So that's basically a system, and if you choose this point, then you get this isomorphism. So I assume this is an admissible covering. Then the theorem is if I take compact cohomology of this f lower star, f upper star of an L-adic sheaf F, then I'm not only in the category of perfect complexes of lambda G modules, but these complexes are also perfect complexes of lambda H modules. And this means that the Frobenius automorphism acting on the compact cohomology over x bar of f star, f upper star of f is an element of K1 of lambda SG. If I take the class of it, if I now apply the connecting homomorphism to it, to the relative K group, what I get is precisely this element here.
Sorry, can you avoid the rest of the board because we can't see a thing here?
Oh, I'm very sorry.
You can move. You can move the.
Yeah, I should leave it. Can you read it now?
I'm sorry, what does the line number 2 say? The first thing, lambda.
So I take the.
Oh, 1 minus f. Oh, sorry.
So I take the. So this is a 1.
So
1 minus the geometric Frobenius. This gives me class in K1 of lambda S of G. And if I take now the boundary of this element, then I get the class that is defined by this complex here.
right. Now, also, your original f was a flat ZL shape, is that right?
That's right, yeah.
Also finally generated, I guess. Is that included in your
Yeah, it's constructible and étale.
constructor?
Yeah. There's one statement missing, which I will explain. So this element LF, and I take the inverse of actually this element. This interpolates L values. And I think I need to explain this statement. So what L values do? Yeah.
Can I ask, when it says it was our main conjecture, it means this theorem?
Yes.
Okay.
I should maybe write this down.
Okay.
So this is the Iwasawa main conjecture. So in the number field case, the Iwasawa main conjecture of the 5 people states something very similar. So you also take something like such a complex here of compact cohomology, and you state that there is a canonical element that has something to do with L values, and that is such that the boundary of this element is this complex here. So this is almost a one-to-one analog of this conjecture. And what is now the connection to L values? So if I have a ZL sheaf, then I can define its L function. If I take the product over all closed points of my sheaf X, and the determinant of 1 minus t to the power of the degree of X, and then the Frobenius automorphism of K of X, so the residue field of X, acting on the stalk of X, and the inverse of this one. And by the Grothendieck trace formula, we know that this can be described as the determinant of the, or the characteristic polynomial of the action of the Frobenius acting on the complex R gamma C over the algebraic closure with values in F, and the inverse of this one. And this is in fact unit in the power series ring, which comes from some rational function. So if you further assume that this rational function has no pole at 1, or more precisely, if we assume that all those groups are torsion,
You mean X or X bar here?
pardon?
You mean X or X bar here?
Here I mean X. So I assume that these groups are L torsion. And under this condition, this element has no pole or zero. And so this element here can be considered, so I can evaluate this element at 1. And then this element is an element of QL star, which is the same as K1 of QL. And if I take the boundary to K0 of ZL and QL of this element, then I get the class of R gamma C XF. So basically what I want to say is that under these conditions I can really evaluate the L function. If I now take some right lambda G module M, then I can tensor my sheaf F lower star, F upper star of F with M. And this is then again a ZL sheaf. And if these cohomology groups are then torsion, then this result by Neukirch and Pila-Bayer tells me that what I get that if I take now the induced map on the K-theory, which is given by tensoring with lambda G of my L of F, what I get is precisely the value of this M, this L-adic sheaf M tensor lambda G F star, F lower star, F upper star of F at the place 1. And you can get all the other places L to the N if you just twist by the cyclotomic character. So this gives the connection to L values in this situation. And now I use the last 5 minutes to give some details of the proof, which is basically a very simple calculations, and the steps are basically all known to the experts, I guess.
What does the formally say if 1 is an eigenvalue?
Are you pardon?
What does the formalism say if 1 is an eigenvalue of the Frobenius?
If 1 is an eigenvalue of the Frobenius, then I have a problem, because then I get a pole, and then the formalism in this shape doesn't say anything.
You cannot arrange it.
No. But the idea is if I pass to the larger picture of the of lambda G, then I don't get any poles. So this is always defined in this sense. So, and I know that this this element L of f interpolates all the other defined L values. And because at almost all places the L value is defined, I really get some nice result. So basically 2 is a direct corollary. So 2 of the theorem is a direct corollary of 1 because of the exact sequence that I had. Because I know how the boundary morphism, what the boundary morphism does on this endomorphism 1 minus f. It just sends it to the cone, and if I have an exact sequence like that, then the element, the cone is quasi-isomorphic to this element. So this is easy.
In your main theorem, you want to say that as the first one belongs to, and this guy corresponds to that of this.
Like fun? Yeah?
And that the second assertion is not finished. The class.
No, it is finished.
Yeah. The statement is that this class maps to this class here.
Well, you always have a problem with unfinished sentences. That's okay.
So, you mean why is this a quasi-isomorphism?
No, it's fine.
Oh, it's fine. Okay. So basically, I'm reduced to prove 1 because 3 is immediate 2. So the first step is we can reduce everything to the case that H is a finite group.
Huh? Air conditioning gone. Why?
What? So this is a proposition that basically can be found also in the paper of the 5 people. So I can choose open subgroup of H, which is pro L and normal in G. Then if I have a perfect complex of lambda G modules, then the following 2 are equivalent. The statement that this complex is perfect as lambda G modules, lambda H modules, and the statement that if I take the derived tensor product with lambda mod G, G mod J, of K, that this is complex in in P H mod J lambda G mod J. And this is also equivalent to the statement that the rank of those the cohomology groups of those this complex over ZL is finite. So we can assume that we are in this case that H is finite. I have just 2 more minutes. So in this situation, I find a subgroup of gamma dash of gamma such that gamma dash is central in G. This is also an observation of the 5 people. But then, if I take now the scheme Y gamma dash and the induced covering F, then this is exactly the cyclotomic covering. And now it's a classical fact that if I take the ith compact cohomology of this cyclotomic covering, or the induced sheaf by the cyclotomic covering, what I get is the I plus first compact cohomology group over the algebraic closure of this Y gamma dash with values in F. And I need to add a projective limit over all n's divided by the nth powers, L to the nth powers of the Frobenius acting on this cohomology group. And since I know that these cohomology groups are finite ZL modules, I know that these are finite ZL modules, and that's all I need by this proposition here. And this completes the proof, or at least the sketch of the proof.
Sorry.
Yeah.
Why did you say those are finite? I didn't quite understand.
These cohomology groups are finitely generated. These here
Right.
are finitely generated cohomology
Yes,
groups.
that's fine. Yeah.
Yeah.
And then, so why does that make that quotient finite?
Because if you take an ZL module, yeah,
Without any assumption on F? I mean,
right?
is that right?
Yeah, should be.
What if F acts trivially on? What if F has eigenvalues 1?
Well, you
Then-
also need that you deal with all the cohomology groups, and you have sort of the multiplication by L sequence and so on, so altogether.
Oh, say again?
But well, if you have trivial action,
Right.
then what you get in the limit is precisely this group here, which is finite as ZL module. So you mod out by nothing, and what you get is the group itself.
Ah, I see. I guess that's okay.
Other questions?
Yeah. Under the assumption that one is not an eigenvalue from the L value,
Yeah.
you recover the whole complex R gamma on X. And does one have conditions to go vice versa? That means knowing the R gamma, can one go back in the exact sequence of, is that conceivable that one can give some restrictions on F on the sheaf in order to predict the eigenvalue out of the R gamma? I mean, a sort of splitting in the K-theory sequence on those terms.
Yeah, I see what you mean. I don't know. I haven't thought about it. Yes?
If I understand correctly, your basic example is one irreducible, let's say, projective smooth variety over Fp, and then you have on one hand the Grothendieck pi 1, and then you extend by the ZL, I guess, cell part of the arithmetic Galois group. And then all this will be true if you don't have the eigenvalue 1. But are there other examples, twisted examples?
You mean
Where you have all this basic yoga that you presented at the beginning? Is it really more general?
well, basically it works really with, as I stated in the beginning,
Yes.
you can just take the an arbitrary L-adic Lie group and take the trivial covering. Then the whole yoga works for this group, for example.
The trivial covering.
Yeah, the trivial covering, which is given by
Or you just take a variety and you make products.
Yeah,
Yes.
genau.
But what does it say in this case?
Yes, that's a good question, and I still haven't had the time to think about this, but that's on my schedule.
But
for
one
the
would
next
assume
weeks.
that the natural situation is the first one. The one where you are saying something.
Yeah, yeah.
Yeah.
But I just finished this part like two weeks ago or something, and so I didn't have the time to think about the rest, which is still open.
So how about L equals P equals the characteristic?
Yes, in this case, things become much more complicated, and there are things known in this case, but I was not working on this. It's more Fabien Trihan and some Japanese, Ochiai, right. Ochiai and Fabien Trihan, which were really working hard on these kind of questions. And of course, what you need there is some crystalline cohomology and p-adic Hodge theory to attack those questions. And so things become much more difficult.
And another question, so what happens if in your definition of covers at the beginning,
Yes?
you allow some ramification?
I've no idea. But I think you really run into troubles there. At least I
Even if
believe.
it's T ramification?
Pardon?
Even if it's T ramification?
No, tame won't cause problems.
Yeah, I haven't thought about these questions either.
So in the connection with L values, there was this assumption that the cohomology is torsion.
Yes.
So what if it isn't, or?
So the basic idea is if you twist with a high power of the cyclotomic character, then you get away from the situation where you have torsion. So in this sense, the element up in the K1 of the Iwasawa algebra still is something like a L-adic L function for this sheaf F.
But that's the same situation. I mean, in the very classical setting of p-adic L function. I mean, you always
right.
interpolate critical
Yeah.
values.
Yeah, that's
Because otherwise you do
precisely
not
the
have to
idea.
say anything. But and here, if you take say a reasonable sheaf, of course, then you understand where the poles are, right? I mean, if you have a pure sheaf, some weight, eigenvalues, then you know exactly. Right, K conjecture.
Yes?
Now, do parts 1 and 2 of the theorem still hold if you just take an arbitrary lambda G sheaf instead of the form pullback push form?
I don't think so, actually. No. Because what I really use here is that this, so you need something, a result of this type, and if you take an arbitrary sheaf, then I just can't get that to work.
Right. So if X is proper.
Yeah. Well, maybe there's some case, but I haven't checked that part. This is all I can prove. But actually, I can prove something more, and that is actually the whole yoga still works if G is not an L-adic Lie group, but only well, something like a topological finely degenerated virtual pro-L group, which means that I find that the L-silo subgroup of my group G is topologically finite degenerated and open in G. And then still everything works. Because in this case, of course, I don't have the result of the canonical OR set of Veliakov, or at least I don't know if it exists. But what I still can define are these K groups there, and I can work with these K groups, and everything goes through smoothly in this case as well.
But then you don't assume that the cyclotomic is in there?
I still assume that.
I suggest we have coffee and tea, and then we resume at 20 to 4.